Welcome back to the Intro to GIS video series. In today's video, we're going to be walking through Lab Activity 2. Some of the labs that we will be completing in this course do not have videos, but the ones that are not as straightforward do. So in this video, we're going to learn how to project spatial data, how to run some basic tools and do a simple spatial analysis. We'll also learn how to join tables and do a field calculation, which will be used to produce some charts and graphs. All of this work will end up in the production of a final professional looking map that you could present to a client or use for some sort of presentation. So to begin today's lecture, I want you to log into D2L and I want you to go to the Labs section of the course content. And I want you to click on Lab 2. And instead of viewing this in the viewer, I would like you to download this lab, because that will give you the opportunity to write your answers directly in this Word document and upload this into D2L as your final submission. So go ahead and click on that download button, which will give you your own version of this lab, and then go back to the labs page, and I want you to download the Lab 2 data folder. Now, it might take a minute for these files to download because they do take up a considerable amount of space. But once your data has downloaded, it should pop up in a Windows Explorer dialog box. Now, one thing that is very important that you pay attention to is that these files are zip files. Zip files are basically a compressed version of that file. So we compress it to reduce the file size, which makes it easier to transfer information, to email it, or to save it on a flash drive. Now, the complicated thing about zip files is that in Windows 7 you can actually view the contents of these zip folders without extracting it or decompressing it. So sometimes people go in and they click in these folders and they try to start working with it without doing an extraction operation. So anytime that you download a zip folder, it's very important that you click the Extract All Files folder. Or button. When you click that button, it's going to ask you for a path to extract the data to. My recommendation is that you browse to your Documents folder, make a new folder in there, call it Lab 2, and extract to there. After the extraction is complete, it should pop up with another window showing you all of the data that was contained within that compressed zip folder. Now that it's been extracted, we can go ahead and begin to use the data in ArcGIS. If you don't unzip it, it will not be visible in your Arc catalog, as ArcMap cannot read or view zip files. Okay, so what we're going to do to start this exercise is go to the Start menu and open up ArcMap. Now, as we progress through this lab, some of the tools or operations may take a little bit of time to run, and it might be helpful for you to follow along with me. So you might want to pause this video at certain times so that you can keep pace with the exercise. So we're going to start off with a new map, and we're going to have a blank map to begin the exercise. The next thing we need to do is go to our catalog, and I want you to make a folder connection to your documents in Lab 2. So I want you to go in here, find your documents, and then find Lab 2, and click OK. And what that does is it gives us a new item in our folder connections that directly links to the Lab 2 folder. Now if we expand those folders, we can see that in here we have several different types of vector information in addition to 2 tables that we will use in this exercise. Now I want you to go to your lab document so that we can review what needs to be done in this exercise. Okay, so for this lab, we're going to pretend that we have been hired as a biogeographer. Biogeographers are people who study the distribution and spatial patterns of flora and fauna. And so in this particular situation, we have been hired to study peregrine falcon reproduction. Now, to give you a little bit of background on the peregrine falcon, back in 20 years ago, 30 years ago, their populations were falling drastically, and they actually made it onto the endangered species list. And many scientists hypothesized that the peregrine falcon populations were being reduced due to eggshell thinning that was likely a result of DDT and other pesticides that were being released into the environment. What? Sorry about that, my connection just cut out for a second. So to go back, we had the peregrine falcon whose populations were falling, and people became very concerned. And in Dinosaur National Monument, there was a peregrine falcon reintroduction program that was launched to try and bring these species back up to levels that had existed before the DDT crisis. So within the monument, there were several places where peregrine falcons' nests were purposely put in certain locations. Eggs were monitored. The development of the species was watched very carefully, and people would catalog the number of chicks produced per nest over certain time periods, and this resulted in a pretty large data set that went back about 15 years. But for this exercise, we're dealing with data that runs from 2000 to 2003. So what we have is we have very detailed information about the number of chicks that were produced in each bird nest, which is referred to as an eyrie for peregrine falcons. The reason Dinosaur National Monument, and here you can see a map of the monument, was a nice place for this reintroduction program is because it was really considered to be prime habitat for the peregrine falcon. These birds like to dwell on cliff edges, and they also like to be within fairly close proximity to a river or water, as a lot of the species they eat live in those areas. So over time, the bird's population has rebounded, but there's very little known about the spatial components that affect this bird's ability to reproduce. So Dinosaur National Monument is a very good example of a place where we have data that we can use in a GIS to look at the spatial distribution and maybe the patterns that could be impacting how these birds reproduce. Another thing that makes Dinosaur National Monument unique is that it has 2 different rivers that run through the monument. One is the Green and the other is the Yampa. The Green River is one that is regulated, so it has a dam, but the Yampa does not, and that makes the Yampa River a very unique habitat within Colorado and the entire Colorado River Basin, because it's only one of 2 unregulated rivers in that region. So this again provides a very unique opportunity to study how these birds reproduce, and maybe even the impacts that a dam has on the reproduction of the species. So what we're going to do is use ArcGIS to explore this data and to try to answer some of the questions that we'll go through below. So here, if we just look here, we have this nice generic map or general map that I've produced showing the different locations of these birds' nests. and they're also labeled with these unique identifiers for each nest. So for example, PC stands for Pot Creek, HR stands for Grand Overhang, um, in Jackson Hole is JH, and so on. And here you can see in this one picture, if you look very carefully, I actually took this from about a mile away. I was on the other side of a cliff, and I identified this bird nest by the white droppings that we see on the cliffs. And if you look in here, you can see right there is a female peregrine falcon, and she actually is feeding two chicks that you can see there in white. And you might have to zoom in on that, but it's a pretty neat picture, and it gives you a little bit of an understanding as to the habitat that these birds live in. Okay, so if we scroll down here, there are a couple different types of spatial analyses I want you to do. And what we're really trying to do is to work with some very basic proximity tools and maybe the measure tool to look at some of the spatial relationships that these nests have and how that relates to the reproductive success of that nest. So what we really want to think about is, is the distance that these bird nests are from each other. Is that a positive thing, meaning it leads to more chicks, or does it result in less chicks? Does the distance from a park boundary impact how many chicks the nests produce? Does distance from a river or the amount of habitat following a river have any impact? So there's many different kind of proximal based questions that we'll try to answer. And then after you've done that, I want you to kind of interpret some of those results. So I want you to think about whether or not the distance that a nest is following something called line of sight, which is basically a straight line distance as the crow flies. Does that affect how many chicks the nest produces? Or alternatively, does the amount of river miles between nests affect reproduction? And then we might talk about whether or not proximity to a park boundary has an impact on these nests. And I want you to kind of explain this in a couple sentences or a paragraph. So don't just give me a yes or no answer. I want you to tell me whether or not you think line of sight distance affects reproduction, and then tell me why. So maybe we could create a graph or some sort of chart that might explain what's going on better, and you can reference those things. So really try to explain your thought process and your rationale. And then lastly, what we'll do in this lab is create a professional quality map, which has labels and different cartographic components that make a map a very useful presentation tool, and that could also be something that you could use for some sort of publication or scientific research. So before we get started, I want to just mention a few things about cartographic elements. So if we look at the map here on the top of the page, you can see that there are several different elements that make this what I consider to be a professional quality maps. Maps are really only useful if they have all the pieces on it to make a user understand its purpose. And so the very first thing that we always want to include on a map to help the user use it is a title. All maps must have titles. All maps must also have a legend, so that people know what the features are on the map and what different colors represent. You also need to have a scale so that people can kind of understand what's going on with the size of an area or how big certain features are. It's also very important to have a north arrow, or you might also have heard it referred to as a compass rose, so that people can orient themselves with the map if they're out in the field. And then you always want to also include your name and also some references on a map. So if you use data from somewhere like the Census Bureau, or you contacted Radford City and got data, it's very important to cite that just like you would in a works cited page or a bibliography. And just like any artist, you would always sign your work. So it's very critical that all maps have your name. So that's basically 5 elements in addition to the map. We have title, north arrow, legend, scale, and then your author and source information. Now, if you can't remember how to add all these elements, you could always reference the map and layout basics lesson that we have, and I'll also go over that later on in this video. Okay, so let's go to ArcMap and let's go to our catalog so that we can begin to add some data. What I want you to do is to browse to your Lab 2 data folder, and I want you to drag over the Dinosaur National Monument layer, the Ivory Locations layer, the Hydrology layer. There's also a Parks layer, which has all the national parks in the U.S. And lastly, we're going to drag over the Reproduction Data table. Okay, now, in my earlier video, I mentioned that there was something called a coordinate system and projection, which gave us information about how the spatial data was recorded. And I also mentioned that there were different types of coordinate systems and different types of projections that we might use for different reasons. Now, again, I'll go into more detail on this in a later date, but what I want you to notice now is that the coordinate system is set for your data frame by the very first layer that you add into ArcMap. So in this situation, the first layer we added was Dinosaur National Monument. Now, if I right-click on Dinosaur National Monument and I go to the Properties and the Source tab, I can identify what type of coordinate system is being used in this data. In this case, it is a geographic coordinate system, and it's called WGS 1984. It also uses a unit that is a degree. So many of you are probably familiar with how a GPS records information, and that's in decimal degrees. We can reference at the bottom of the map the units that have been set based on the first layer we added to the table of contents. So all of our spatial information is being recorded in decimal degrees, and because, again, this was the first layer, it set our data frame, and we can go in and right-click on Layers and go to Properties. It set the coordinate system of the data frame to WGS 1984 as well. Now, WGS 84 is a very common coordinate system that you'll run into, but this is more designed for doing types of spatial analysis that happen on a global scale. So this coordinate system has really been designed to deal with three-dimensional data at the global scale, and it's really not suitable for analysis that we do at the more local scales, so maybe at a state or regional level. So because of this, we're going to need to change the coordinate system into one that's more appropriate. And to do this, we're going to run the very first tools that you guys have probably used in this course. So before we do this, we have to pick a coordinate system. And in this particular case, because Dinosaur National Monument crosses the Colorado and Utah border, we cannot use a coordinate system that is designed for the state scale. Instead, we'll have to use one that is more appropriate for the regional scale, and that would be something called the UTM coordinate system, which stands for Universal Transverse Mercator. Now, the UTM coordinate system is broken up into a series of different zones. So before we pick which coordinate system we're going to actually use, we're going to have to go out and identify which zone is most appropriate. The easy way to get a map or a grid of UTM zones is to do a quick Google search. So we'll go in and we'll type in UTM zones for the US. And here we have, let's see, we'll go to the UTM Wikipedia one, and we'll click on this image. And here we have a large map that shows all of the different zones that are global. But because we can't actually see state boundaries in this, it might not be perfectly appropriate. So there are other ways using ArcGIS to better identify which UTM zone you might want to use. So I want you to go back into ArcMap, and we're going to click on go to the catalog, and we're going to make sure that we have a folder connection to the C drive. So if you don't have one there yet, I want you to go to the Add Folder Connections and map directly to the C drive. And Esri has provided us with some basic reference files that we can use to identify what UTM zone or other coordinate system zone we should use for our data. So to access this, we need to go into our program files, use the times86 folder, which basically stands for the 32-bit folder, and we're going to scroll down until we find ArcGIS. No, that's not right. Until we find Esri. Oh, I might have told you wrong. We're not going to go to the 86 folder. We're going to go to the standard programs files folder. And it's hidden from me today. See program files. Oh, okay, it is in the 86 folder. Program files, ArcGIS, desktop, yours will say 10.1, and then if we scroll down, we should see a folder for reference systems. And in reference systems, we have a layer for the UTM zones. I want you to add this to the map. Now I want you to notice in my table of contents that it changed from order view to source view because I added some data that was in a different folder than all of my other lab information. And when this happens, you can no longer reorder your things. So we need to go click on the order view, and I want you to drag the UTM layer to the bottom of your table of contents list. That way we can clearly see where Dinosaur National Monument is, and by using the Identify tool, we can click in the map area and we get a reference telling us that this is Zone 12. And because this is in the Northern Hemisphere, it will be UTM Zone 12 North. So now we no longer need this UTM reference layer, so I want you to right-click on it in the table of contents and remove it. It's always good to keep your table of contents nice and clean and organized. Okay, so now I'm going to zoom back into my area, and we're going to run the projection tool to turn all of our data into UTM, into the coordinate system UTM Zone 12 North. So I want you to click on Arc Toolbox, go down to Data Management Tools, Projections and Transformations, and then we're going to expand the Feature toolbox, and we're going to run the Project tool. We're going to start off with Dinosaur National Monument, and I want you to drag that over into the input data set, and notice how it's identified what the input coordinate system is. It's writing to my default geodatabase, which in this case is OK. And the only thing we have to pick is an output coordinate system. So I want you to hit the Browse button, go to Select, and we're going to pick a projected coordinate system. Projected coordinate systems are designed to retain the properties of size, distance, area, and shape. So based on what we pick, certain types of properties will be retained. So we're going to go projected coordinate system, UTM, And we're going to pick NAD 83. NAD 83 is identifying the type of datum that we're going to use for this coordinate systems. Again, I'll go into more detail about datums later, but for now what I want you to remember is that a datum is a mathematical model that represents the size and the shape of the Earth. And because of plate tectonics and maybe mass wasting and erosion, the size and shape of the Earth has changed over time, and that's why you'll see NAD 27, 83, 84, and there are even 2010 and 2008 ones that exist now. But NAD 83 is by far the most common, so that's the one that we're going to go with. So I want you to click on NAD 83, and I want you to find UTM Zone 12 North. Hit the Add button, and we'll click OK. It's telling us that there's a geographic transformation that needs to be used. In this case, we're going from WGS 1984 to NAD 83. So we're going to select that option and click OK. Okay, now notice how a new layer has popped up with PRO at the end of it. So this is my projected file. Now, if you look at the map, you might be thinking, well, nothing really looks that different, but it is different. The reason that you can't notice it visually is that ArcGIS with version 10 does coordinate system and projection transformations on the fly. This can be very nice for visualizing data, but you will run into problems when you're actually running tools. So don't get comfortable with the fact that things visually look okay, because they might not be. I mean, one of the places you can go to make sure that you do not have a coordinate system or projection problem is page 38 in our book, which gives you some clues about identifying whether or not you have a projection problem. So now that we've projected the Dinosaur National Monument file, I will go ahead and right-click on the old one and remove it, so that again I keep my table of contents very clean. Now I want you to go through that same process for the parks file. And we'll remove the old parks. Then we'll do the hydrology file. But what we're going to do a little bit different here is we're going to import or steal a projection from another layer, and this can be a very helpful time-saving technique. So again, I want you to hit the Browse button, but instead of going through that big long list, we can simply hit Import, and I will find the data that I've already projected. So in this case, it would be Parks Project. Again, we'll pick the geographic transformation. And this one takes a little bit longer because there's a lot more data in the hydrology file than any of the other ones. And again, I'll remove the old one. And then lastly, we'll do eyrie locations, which are the nesting locations. Again, we'll pick the appropriate transformation. And I will remove the old one. Now, you might have noticed that when those tools were running, that an error did pop up, and it said that there was a datum conflict between what my projected data was in and what the data frame was set at. Now remember that the datum is the mathematical model representing the size and shape of the Earth. Our old data was in WGS 1984. This data is in NAD 83. So what's going on? Well, what happened is the data frame is always set to the first layer, to the coordinate system of the first layer that you add to the map. So this is still in WGS 84. You can identify this by looking down here and seeing that we're in decimal degrees, or by right-clicking and going to Properties and reading at the data frame properties. We see we're in WGS 84. It's always good to match your data frame coordinate system to your layers if you go through the projection process. So I want you to set the data frame coordinate system in the same way that we picked the coordinate system for our projection tool. So we'll go into Projected, UTM, NAD 83, and UTM Zone 12 North. And I'm going to hit the Apply button. Now, UTM is in meters, and our old data was in decimal degrees. But you'll notice that these map units are still in decimal degrees, which is a little misleading. And so what you need to do is you need to go back into the properties of your data frame and set your map units to meters. And we can see here that the map is in meters, but the display was in decimal degrees. So you have the opportunity to switch things around a little bit. Some people like to set it to miles or feet, but in my opinion, best practice is to always match map units to your display units, and all of these problems can be alleviated a little bit if you run your projections before you actually add the data into the table of contents. But it's still a good exercise for you guys to go through. So we'll hit the Apply button and we'll hit OK. And we can see that my map units are now in meters. And if I move my cursor, I get different coordinates based on their location. And you might also have noticed that the map has rotated a little bit to the left. And this has happened because, again, we're using a slightly different technique or system for modeling spatial information. Okay, so for now I'm going to go ahead and turn off my parks layer. And I'm going to do a little bit of changes to my symbology. So I'm going to go I'm going to double click on this square in the table of contents, and I'm going to make Dinosaur National Monument hollow, and I'm going to bump the size up to 2, and I'm going to make the color, I think I'm going to make the color orange. So now I can kind of clearly see this boundary. And you know, for you guys, you might not know very much about this terrain or the topography or the land cover, so we're going to want to get some sort of base map. And one great place to go get base maps is ArcGIS Online. This can be accessed by going to File and ArcGIS Online. And what I want you to do is I want you to type in the word imagery. And this is going to go out to the web, and it's going to look for base maps that provide us with some imagery or some aerial photography of the layer. Now you need to be careful and select one that has the add option and not the open option. So I'm going to go here and I'm going to pick this world imagery layer, and I'm going to hit the add button. And it's going to drop this base map in at the bottom of my table of contents and provide me with some much more detailed information so I can kind of understand the geography of the place. Now the one downside to these ArcGIS Online layers is they are streamed over the internet, so sometimes they can slow down the performance of your map, but they're still very good to have. Well, as I mentioned, they can slow down the performance of your map. And this one appears to not be working, so I'm going to remove this and find another one. But before I do that, I'm going to save my map document. And this is because ArcGIS has a tendency to crash on you, especially when you start getting involved with lots of data and lots of processes. So I'm going to right click on my base map and hit remove. And then once this operation is completed, I'm going to go up to the File menu and save this map document. So similar to Microsoft Word, we refer to a mapping project as a map document. The thing that's a little bit different between Word and ArcMap is that all of this data is not contained as part of the map document. It's only listed as a reference. So many times people will save a map document on their computer, and then they will move to another computer and open it up, and they're surprised to see that there is no data there. And this is because you need to move your data and the map document over or across machines. So there's two components. There's the data that you use in the map and the map document itself. And you must have both components all the time or you can't switch computers or devices. So while my computer is thinking, it's not very happy with me. Sometimes when ArcMap gets stuck, it's useful to hit the Control-Alt-Delete and to fire up the task manager. And for whatever reason, this operation or process, as it just did, kind of gives it a little kick in the butt and makes it do what you want. So I'm going to go now up to the File menu and hit Save As. And I'm gonna stick this where all my data is so that I don't get confused. So I'm gonna go to My Documents, and I'm gonna find my Lab 2 folder, and I'm gonna store this inside of this, and I'm gonna call this Lab 2 Dino. Remember, never use any space in any file name for GIS. So to kind of re-emphasize the difference between a map document and your data, we can go look in our Lab 2 folder, and we can see that we have all of our different layers, right? And then we have Lab 2 in there. So this map document references the layers that we're using. You have to have all those, or it just won't work. Okay. So, we're going to go back to ArcGIS Online now, and we're going to find a better imagery map. So I'm going to type in, this time, World Imagery, and hope that I can find a better ArcGIS Online service. So we'll use this one right here, the map service provided by Esri, and I'll hit the Add button, and we'll cross our fingers. All right, great. So now you can see we have some aerial photography where if we zoom in to an area, it can help us kind of understand what's going on geographically there. We can see the terrain, we can see the type of land cover, and other things. So it's very helpful when you're working in an area that you don't know much about. Now, one of the interesting things that happens when we zoom into this part of the map is that we can kind of see that the rivers don't exactly line up with the imagery. So to better visualize the rivers, I'm going to double click on this line, and I'm going to bump the line width up of my rivers to 3, and I'm going to click OK. And so now we can see that, you know, this roughly follows the course of the river, but it's not exactly perfect. And so one of the things you really need to remember about when you deal with GIS data is that these layers we use are representations of features on the surface of the Earth, and they're not always perfect. Lots of times they're generalized or simplified so that they don't take up as much data. And in this case, we could very clearly say that the data has been generalized, and you can see this by the roughness or the jagged lines where a real river is flowing and very curvy. It's just very hard to represent that at certain scales, but that's okay for the purpose of this exercise. So what I'm going to do now to boost up speed, because I'm streaming this live, is I'm going to turn my imagery off so that I can use it at a later time, and I'm going to zoom out a little bit using the scroll wheel on my mouse. Now I don't exactly like the line width of my river, so I'm going to go back in and click on this, and I'm going to bump that down to a 2, which is, I think, a little more appropriate. But what I'm noticing now is that it's kind of hard to see these Imagery locations because the green is not a very good color on top of the blue. And for you guys, you might have different colors because these things are randomly generated, but you can go in and manipulate them on your own. So instead of green, I'm going to turn my Imagery locations into red, and I'm going to click this circle 1 option, and I'm going to go down to a 16 or 14 size, and I'm going to pick red and hit OK. And now it's much easier for me to actually see where these Imageries are in reference to the rivers and everything else. The one thing I can't see though is labels, so I don't know which Imagery is what. One way to identify an Imagery is to go in and to click on it using the Identify tool. And what it did right there is it actually identified Dinosaur National Monument. So what I'm going to need to do is change the layer that I want to identify. And so I'll go in and I'll pick Imagery locations. And now if I click on that, it tells me that that name is GL, and it also gives me an X and a Y coordinate for that, which is nice. But I don't want to have to click on all of them when I'm doing my analysis. So instead, I'm going to label these features. And I can see here that there's a field name called Imagery name. And so one way to kind of explore data is to use the Identify tool, but the other way is to actually look at the table itself. And we call tables in GIS attribute tables. And you might remember from my previous videos that all of this data has a spatial component and a tabular component. So it's very important before you engage in analysis to explore the tabular component. We can do this by right-clicking on the layer of interest and going to Open Attribute Table. And we get the same information that was presented in the Identify tool, but in a different context. We can just see the whole table itself. We see there's a unique identifier. It's telling us the type of vector information it is, and then we have these different fields. So this would be an example. Oh, I'm sorry, let me move this over here for you guys to see it. This would be an example of a field So this is the Y field and the X field and the Imagery name field. Now let me do some table management so you can see my screen better. There we go. Now what's really nice is that these records, or as we call them, rows, so this would be a row and this would be a field, these rows are linked to the map. So I can click right here and highlight a row, and look what it does. It also highlights the feature on the map. So this one is PC, it's highlighted on the map. And you can go through and highlight all of those, which can help you identify features. You can also hold the Shift key and select more than one record, which is nice. Okay, so now we know that we have this nice identifier called Imagery name, and we probably want to label our features using that. So we're going to go over to the table of contents and right-click on Imagery locations, and we're going to go to our properties. Now remember that this layer properties allows us to, for example, change the name of something, to look at the source, and so we can remember that we put this in UTM Zone 12 North, We can also change how it looks, just like we did through clicking in the table of contents. And we can access the Label tab to turn on labels. So I will check label features to turn them on, and I will make sure that the label field is Imagery name. Then I can hit apply, and we have labels pop up. It's very nice. Now there's a shortcut to turning labels on and off, which involves right-clicking and going to label features and turning them on or turning them off. So remember, there are many ways to do things in ArcMap. Okay, so now we're in a good spot. Because I highlighted some records in my table, you'll notice that I still have these cyan colors on the map. This is something we refer to as a selection in ArcGIS. Before I move forward, I want to clear my selection because tools will always run based off selected features. So I'm going to go to my menu bar area, and I'm going to hit clear selected features. And now I'm working with a nice empty slate. The other thing I think that I want to do is turn the labels on for my rivers so that I know which rivers are what. And I will right click and go down and hit label features. And now I can see that this is the Yampa and this is the green. Right? Okay. So now what we're going to do is we're going to go to the Lab 2 document, and we're going to look at the very first question and see how we can answer that. So we want to know how many iris and also which ones are greater than 5 miles outside of the park boundary. So whenever we're dealing with questions that have a spatial context, it's always good to kind of say it out loud and think, okay, you know, does this make sense? What's going on? And what tool might work the best? And you need to think logically about the outputs and if they make sense. So far we've learned how to run the buffer tool, and to me that sounds like a really good option. So okay, let's run the buffer tool and see if that gives us something that we can use. So we want to know how many nests are 5 miles out of the park boundary. So I'm going to go to my toolbox, and I'm going to go to Analysis Tools, and I'm going to go to Proximity and Buffer. Our input feature to start is going to be Dinosaur National Monument. I'm going to drag the input feature in. It's going to send it to my output class, and the buffer operation is asking for a difference, and it wants, for this question, we want to know if it's 5 miles outside of a park boundary. So I'm going to go here and put 5 in and change that to miles, and I will run this tool. See what happens. Okay, so what we have now is a buffer that extends 5 miles outside of the park. And so by referencing this, it's pretty easy to identify which one and also how many of them are not in the park boundary. So that's one option towards answering that question. Now another way to think about this is to go 5 miles from an iris itself. So I'm going to go back to the buffer tool, and instead of using Dinosaur National Monument, I'm going to use the iris, and again I'm going to run 5 miles, and I'm going to run the tool, and we get a slightly different output from this one, which is a little bit harder to interpret, but it kind of does the same thing. So to simplify the interpretation of this, I'm going to make that layer hollow, and I'm basically looking for rings that intersect the park boundary, and there's only one in particular that does not intersect it. So we actually used 2 different types of operations to come up with the same answer for this question. So it's nice to explore different options. Now the other thing that you could do is to actually use the measure tool and to actually measure how far away things are from this park. And so for the most part, we can see that that there are many of the nests inside the park. So there's only two that we have to actually measure. So we can click on Cross Mountain and measure to the closest point. And we can see that the output is in feet, so we'll need to change that into miles. So that one's 7.18, and we can hit escape to do or double click to start a new one, and then we can go to CR, and we can go over to there, and we can see that it's 4.01. So it's very close to 5 miles, but not exactly. So the measure tool is an example of a less precise tool than the buffer tool, but still you would have come up with the same answer. So that's an example of how to approach question 1. Now question 2, we want to know which eyrie is farthest away from a river or a stream. So we can look here, and certainly there's some visual interpretation that you can do, but again, the measure tool might be handy so that you can actually quantify the distances. So for example, Jackson Hole is 1.12 miles, whereas Pot Creek is a half a mile, and RP is again a half a mile. So you can do visual interpretation, but when possible, I always recommend that you use a more precise tool. Okay, so now we'll go on and look at question number 3. So now I want to know which ones are closest together following line of sight. Now, when we talk about line of sight, I want you to think as the crow flies. So you might talk about the distance from Radford University to DC, and we might say that it's approximately 300 miles. But if you actually have to drive there going down the road, it might be longer because the road is curvy and it twists, it goes through mountains, and so following the road would not be line of sight. Line of sight would be a straight line distance. So if I want to measure the distance between GL and PC following line of sight, I could click on this dot and measure a straight line to that dot, and we can see that we're 4.175 miles apart. Whereas alternatively, I could look at how many river miles exist in between those places. And to track river miles, you might have to zoom in, and we can see that, well, these things aren't exactly on the river, but we can approximate it. So I might start here, and then I would follow, and you can click along this line, and you get a total length in your tool. I could follow the length of this river, and I see that we're 4.7 miles following the length of the river. So here again we're 4.1, and following the river we have 4.7. So there's actually more river miles in between these two places than straight linear distance. And this might be important because you have situations like this one in between Geo and HR, where they're really close together, but there's a lot of potential river mileage in there that's prime hunting and habitat area. So one could speculate or hypothesize that maybe the distance of a nest from another following line of sight is not as important as following the river. But we don't really know because we haven't done enough analysis yet. But that's one potential option for dealing with question 3, where you want to know which ones are closest together following line of sight. Another option is to run a different type of tool called the near tool. And the near tool is a little bit different than the buffer tool because it doesn't create a new output. Instead, it adds an entry to the table that you run of the layer that you run the tool on. So again, I'm going to go to my toolbox in proximity, and I'm going to run the near tool. And you can always click on the show help button so that you can kind of determine the best way to run this tool. The way it basically operates is it takes an input feature and it looks for the closest object from a near feature. So it says, hey, what thing is closest to me? And then why don't I measure that distance? So in this situation, our input feature will be the eyrie nests, and we want to know which ones are closest together, so the near feature will also be the eyrie locations. And then we can run this tool, and then open the attribute to see the results of it. So if we scroll over, you can see we have a near FID and a near distance. Now the distance field is in meters, and it's going to reference whatever we have down here in the bottom right hand corner. So what this is telling me is that the feature that has an object ID of 1 is closest to the feature with an object ID of 2, and it is 6,700 meters away. So what we can do is we can highlight those two, or we can simply reference the eyrie name. So we have PC and GL, and we know that they're 6,700 meters away. So the question is really dealing with which two are the closest. And what we could do is we could right-click on this field name, and we could sort it in ascending order so that the smallest number is on top. And we can see here that it's these two features that are the closest together following line of sight. So that's how you can approach answering that question. Now, question number 4 is a little bit more tricky, and that will involve actually using the measure tool and you guys manually recording the distances between those eyries following the river, because there's no simple solution for solving that one. Okay, now we're going to move on to question 5, which has to deal with how many eyries are 1 mile or less from the park boundary. Now, this is a tricky one, and it's a little bit different than question 1. Notice question 1 asks 5 miles outside of the park boundary. Well, question 5 is 1 mile or less from the park boundary. And spatially, these are two very different questions. Not just because one is 5 miles and the other is 1 mile, but because one has to do with an operation of being inside or outside, and question 5, we don't really care if you're in or out, we just want to know how close you are to the actual boundary. So you could be inside in less than 1 mile, or you could be outside in less than 1 mile. So let's go and do a similar operation to what we did before, and let's run the buffer tool. And since it has to deal with the park boundary, we'll use the Dinosaur National Monument file, and I'll put in 1 mile. And what this does is it gives us a buffer that extends 1 mile outside of the park boundary. So in this particular situation, this buffer operation does not do exactly what we need. It was close, but because of the type of data it is, meaning because it's polygon data, the buffer operation only goes one way. It only goes outside of the polygon. It doesn't go inside of the polygon. So that particular output isn't going to help us solve this question. Instead, we can use an alternative method, and we can run the buffer on the eyrie locations, and we can make it 1 mile, and we can look for places where that 1 mile buffer intersects with the park boundary. So now I have a 1 mile ring around each of my eyrie locations, and we can search for places where those intersect the park boundary. So this one's okay, this one's okay, 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 not okay. So this one and that one and these over here all are 1 mile or less from that park boundary, and again, that could have something to do with reproduction, so I want you to kind of think about that. So up until now, we've looked at the spatial relationships of these features in regards to park boundaries, to each other, and to the rivers, but we don't really know much about how successful these nests are or how many chicks have been produced. So that's going to be the second part of this exercise. So I want you to go and I want you to look at the attribute table of Ivory locations, and we can see here that there's no real data that's relating to the number of chicks that have been produced. But if you recall from the beginning of the exercise, we added a table called reproductive data. But we can't see that in our order view in our table of contents. And that's because tables are only visible in the source view. So I want you to change views, and we can see down here we have a table called reproductive data. I want you to right click on that and open that table. Notice how it replaces the table that we already have opened. And this is kind of a pain, but there's a solution around that. But what's more important is that we see that there's again the Ivory name, and then we have the number of chicks produced over the various years. So what I need to be able to do is to look at both these tables and to see if there's some way to link or join them together. This can be done by going down to the lower left-hand corner, clicking on another table of interest, and then you can drag it over like that, and you'll have two tables that pop up in a split view. And so I can look here and look, voila, I got Ivory code with this unique identifier, and over here I got Ivory name. So what this means is that I can join the two tables together based on this unique identifier. And join operations are very important in GIS because many times we have information such as address or customer data where there's a name or a social security number or an account number, and we need to link that number to a feature on a map. We do this by doing a join operation. So the join is done by right-clicking on the feature of interest. In this case, it will be Ivory locations. We right-click. We go down to join, joins and relates, and then join. And this will be a table join where we want to join attributes from a table, and it's already intelligent and it's identified that there's only one standalone table, and it's saying, hey, pick a field that exists in both tables and that's unique. And so we know that it's Ivory name in one, and then it's smart, it's identified the only potential match is Ivory code, so it's already populated that other list. And we're going to want to keep all the records, and it's always good to make sure that you validate your join to make sure that it works. So it said, hey, look, there's 11 records, and we matched all of them. So you'll say, okay, that's good. Hit the OK button. Then we're going to close this table and go back to Ivory locations and open that. And what we see is now we have one merged table where we have the number of chicks produced. So one way to kind of look at the reproductive success of these nests is to look at each year individually. But that could kind of complicate things. And so for simplicity, why don't we just look at the total success of these birds over the 4-year period. And to do that, what we're going to do is create a new field and do a field calculation in there to come up with a new reproductive statistic. So one way that we manipulate tables is to go to the upper left-hand corner of the table and click on Table Options. And you'll notice that there's the options to add a field. So we'll click Add Field, and then I want you to type in some chicks. Make sure you have no spaces in any field name ever. And then it asks us what sort of type of data do you want this to be. And what we're going to pick is a double, which is a format used for numbers and is very flexible. So in most situations, I would suggest picking a double. It will solve a lot of problems. So we'll click OK. We see that there's nothing in there, right? It's an empty field, so we have to do some sort of calculation in there. And one of the nice things with ArcMap is that we have a field calculator, which allows us to do very complex math or simple math in a field, similar to how Excel does formulas. So we'll right-click on the field of interest, and we'll go to Field Calculator. And what we want to do is we want to sum up all the chicks that were produced over this time period. So we'll scroll down in this list of fields until we find these four right here, and we'll double click on the field of interest, and then we'll hit plus 2001 plus 2002 plus 2003, and all we do is hit OK, and we have a new field with the total number of chicks that have been produced over that time. Now, in addition to the sum, you might want to have the average, and we can do that the same way by going in, adding a field. I'll type in average chicks. We'll make it a double. And then this time we'll go right-click on the average field. And since we already have a sum field, we can use that. We can click sum chicks divided by 4. And now we have the average number of chicks produced per year. It's pretty handy. So now, how do we visually see the number of chicks that have been produced? There's a couple of different options. I'm going to turn off my buffers so that I just have my basic data, and I'm going to re-symbolize my Imagery locations based on a field. And this is another really powerful thing you can do with ArcGIS. So I right-click on the layer, go to Properties, and I click on Symbology. In this situation, I don't want to do a single symbol. Instead, I think that I want to do a proportional symbol or a graduated symbol. We'll go proportional. No, we'll go graduated, which is located under quantities. And I'm going to use the field that's my sum chicks. And notice how the small ones are a smaller symbol, and the more chicks produced, the bigger the symbol. And maybe instead of 5 classes, I only want 4. And I'll hit OK. And now we can see that the size of the dots is actually related to the number of chicks produced. And this can provide us with some new insight into which nests have been more successful than others. Now what I'm going to do is I'm going to right-click on this layer and copy it, because I want to make a couple other ones. So I'm going to now right-click and I'm going to paste that. So now I have 2 Imagery location maps, and I'm going to turn one off. And I'm going to right-click on this and go to Properties. And instead of the sum, this time I'm going to use the average. And I'm going to change the colors on those so that I can toggle between the two to identify any differences. So now we'll turn both of these on, and we can kind of click on and click off, and they don't really look drastically different. So that may or may not provide you with much help. But another thing you might be able to do is to look at the variation between years. And so we can also symbolize features using a chart. So if you click on the chart option, and we're going to go to the bar column, you can actually send over multiple fields. So we can send over the 2000 chicks, the 2001, 2, and 3. And we can double click on these symbols to actually change the colors, which can help us differentiate between values and years. So now we have 4 different colors, and we have 4 different bar graphs. Okay, so we'll hit OK. And so now we have these nice bar graphs that sit over top of our Imagery nest, and so we can kind of say, hey, look, in 2000, what happened over here? There were no chicks in year 2000 at BJ, or at Anderson Hole in 2002 there were no chicks. And so now we have added the spatial component, the tabular component, but we also have a temporal component because we can look at how these things have changed over time, which is again a very powerful tool and analysis technique. So, what we've given you, or I've done here, is I've demonstrated several ways to answer these main questions, And so what I want you to do is to kind of take it a step further and think kind of deeply about these questions and use the different outputs and data that we've come up with to draw some conclusions of your own. One other thing will show you very quickly is how to make a chart using ArcGIS. And so we're going to go back to one of our Imagery locations, and we're going to open the attribute table. And if you click down on the table options, you should have the ability to create a graph. Now, the only data that we have that's useful in here for a graph is the near distance output, which tells us how close nests are, and maybe some of the chick data. So we're going to go to Create Graph, and we're going to pick a scatter plot where the Y field is going to be the sum chicks, and the X field is going to be the distance that these nests are from each other. So what we would, if we thought that distance had a positive, so the further away the more chicks, we would expect maybe a line to go like this, or if there was some sort of negative relationship, we might expect something else. So we can kind of explore the data a little bit through this graph. So what we see here is that the two nests that were furthest away from each other, were second highest in the number of chicks produced, whereas the most chicks came, were somewhere in the middle. So while there is some relationship, it might not be that positive, or might not be that strong of a relationship. So you might want to explore other things. So maybe something else is going on other than distance from each other. Maybe it's river miles, maybe it's proximity to a park. The list actually goes on, and so those are the sorts of things I want you to think about. I've given you lots of different metrics and visualizations that you can use to come up with these answers, and so put some thought into it and try to use this example to come up with some useful explanations. So the last step for this lab is going to be for you to make a professional quality map, which will involve you going to the layout view. And in this case, I suggest changing your page layout from portrait to landscape, which can be done by going to File, Page and Print Setup, and we'll pick the landscape option. And then you can click on these boxes to resize your map, all right? And then using the Insert menu bar item, I want you to insert a title. I want you to insert a north arrow, a scale bar, and all of the other important components to a map. I want you to make this as professional looking as possible. I want you to think about reducing white space and making a map that helps supplement maybe your discussions. And if you actually reference the Lab 2 document, you will see that there are several requirements that I want you to use. So you have to have the monument boundaries labeled roads. I would like a proportional symbol, but you can also expand on that. And if you happen to have any tables or charts or other supplemental graphs, you can include these in your submission. And so to submit this exercise, what I need you to do is to type all of your answers in a Word document, and then I want you to export your map by going to File, Export Map, and you can save this as a JPEG and then insert that into your Word document. So you'll have one submission with all of your typed up answers in the Word document, and I want you to put that in D2L and name it appropriately. That's all for today. I know that was a long lab video, but we covered a lot of topics, and this really introduces you to a lot of different types of analysis and techniques that we will use quite frequently in this class. So good luck, and if you need to contact me, please email me, or I will be available on Google Plus for some virtual chats. Thanks.